Here's a lesson for section 2.3 and 2.4. In this lesson, we'll learn how to make scatterplots and also how to analyze trends in data by looking at scatterplots. So far in this chapter, we've looked at how to make hypotheses about the relationships between variables, and we've also learned how to conduct surveys by using different sampling principles in order to test those hypotheses. So before we actually look at scatterplots, we need to make sure we understand the difference between an independent variable and a dependent variable. Okay? An independent variable, we can write the definition here, is a variable that affects the value of another variable. Okay? And a dependent variable, opposite to that, is a variable that is affected by some other variable. So when we're analyzing relationships between variables, one of the variables is always going to be our independent variable, and one of our variables is going to be our dependent variable. So to say that in another way, one of the variables, okay, is going to affect the value of the other one. Okay? So our independent variable is going to affect the value of our dependent variable. So as our independent variable is changing, that's going to affect the value of our dependent variable. Okay? And so you can say, in another way, you can say the dependent variable depends on the independent variable. It's affected by the independent variable. Another thing that's important to note here, we use a common letter to represent these variables. Whenever we're representing the independent variable, we use the letter X. And to represent the dependent variable, we use the letter Y. Okay, so always use X for the independent variable, Y for the dependent variable. Let me give you an example here that might help you see the difference. So I'll make my example. Let's say we look at the relationship between age and height. Okay. So I've got two variables here. I've got age and I've got height. Okay? One of those variables is going to be the independent variable, and one of those is going to be the dependent variable. Let's move this up to the side here so we can see it better. So I need to figure out which one is my independent and which one is my dependent variable. So I need to ask, this is a question I always ask myself. To figure it out. So does height depend on age, or vice versa, does age depend on height? Okay, if you think carefully about those two statements, okay, your age doesn't depend on how tall you are. Okay, just because you stop growing doesn't mean you're gonna stop aging. Okay, so your age is gonna progress no matter what happens to your height. But your height does depend on your age, okay? There's a direct correlation to that. So as you're aging, your height is going to increase, okay? Think about it. As a baby starts to get older, their height is going to increase, okay? Up until a certain point, of course. But a person's height does depend on their age, okay? The age is the variable that affects the height, okay? And the height is affected by the age. So my independent variable is age, and my dependent variable is height. The height of a person depends on their age. Okay? So now let's look at this. I've got a table of data here. In this column here, I have the number of hours John studies for, and in this column here, I have John's test score. The first thing I want to do is I want to determine which one of these variables is the independent variable and which one is the dependent variable. So I'm going to ask myself that same question again. Does the number of hours John studies for depend on his test score? Or does his test score depend on the number of hours he studies for? Okay? I think the number of hours, his test score depends on the number of hours he studies for. So his score depends on the hours studying. So his score is dependent because it depends on the hours. So his score is dependent on the number of hours. That makes the hours studying the independent variable because that affects his score. I'll squeeze this in here, hours of studying. So the independent variable affects the dependent variable. So as the hours of studying changes, that affects his score. And you can see that's what happens. As his hours of studying goes up, that increases his test score. Okay? Another trick I want to tell you, if you have a table like this in 2 columns, the left column is always your independent variable. It's always your x. Okay? And the right column is always your dependent variable. That's your y. So if you're given the data in a table, you can determine which one's independent and dependent just by looking at which side of the column the variable is in. If it's on the left side, that's your x, your independent variable. On the right side, that's your y, your dependent variable. Okay. Another way I'll talk about this, just to clarify, you can think, okay, does the number of hours John studies depend on his test score? Well, it can't depend on his score because he studies before he even knows what his score is. Okay, so his test score has to depend on the number of hours he studies. So if it depends on the number of hours he studies, it's dependent on that, so it's your dependent variable. Okay. Next one. So I've got number of guests and meal preparation time in a table of values here. Okay. So I know right off the bat, like what I just said last time, the left column is always your x, which is your independent variable. So I know right off the bat, number of guests is my independent variable. Number of guests. And I know the right column is the y, which is the dependent variable. So meal prep time is the dependent variable. Meal prep time. Okay, and let's just make sure that this is right just by thinking about it the same way we've done with the other ones. Okay, does the number of guests that are going to come to, I guess if they're having a party of some sort or a banquet or whatever, does the number of guests depend on the meal prep time? Like, so if you stay in the kitchen for hours and hours and hours and hours and hours, does that mean that more people are going to show up? No. Okay. Or does meal prep time depend on the number of guests? That makes sense because the more guests that come, the more time you're going to have to stay in the kitchen prepping the meal. So meal prep time depends on the number of guests. So meal prep time is dependent. Okay. So how are these variables related? Well, let's look at the data. As the number of guests increase, so does the meal prep time. So let's just write that there. So the more guests you are having, I'll type this one here. So the more guests you are having, the longer it takes to make the meal. Okay, and that makes sense. I think we forgot to do this for the last question, so let's just skip back there quickly and do that now. So how are these two variables related? So I've got the hours of studying and his test score. I think I mentioned this, but you'll see as the hours of studying goes up, so does his test score. So let's just jot that down. I think I'll say the more you study, the higher your test score will be. And that makes sense as well. The more you study, the better you'll know the material, the higher your test score will be. All right. Now let's look. So in the previous two, we had a table with the information. Now let's look at if we're given the graph. Okay, I'm given a graph of information here. On the graph, I have a number of pizza toppings and cost of pizza. So those are my two variables. I need to figure out which of those variables is independent and which is dependent. So let's ask ourselves the question again. Does the cost of the pizza depend on how many toppings? Or does the number of toppings depend on the cost of the pizza? And hopefully you're starting to get the hang of this, and the first one will make more sense to you. The cost of the pizza depends on how many toppings you put on. Like if you're ordering a pizza, the more toppings you put on, that's going to affect the cost of your pizza. Okay? The cost of pizza depends on the number of toppings you get. So it's dependent. Okay? Dependent variable is the cost of the pizza. And the independent variable, the variable that affects the dependent variable, is the number of toppings. Okay? Number of toppings is independent because it affects the cost of the pizza. And the cost of the pizza is affected by the number of toppings you put on. So how are these two variables related? So let's just jot this down quickly as well. You'll notice that from the graph here, the more toppings you put on, the higher the price. That's why the graph rises up to the right. So I'll type that here. More toppings result in a higher price. And there's lots of ways you could say that, okay? Let's make sure this is bigger so you can see it. More toppings result in a higher price. All right, so let's just, one more thing we'll do with independent and dependent variables to make sure we have the hang of this. Just see if I can, I think we've got all of it there. Okay, so let's fill in the following chart using our understanding of each type of variable. So there's lots of different answers you could have for this, but I'll just show you what answers I might put for these. So if the independent variable is the number of gallons in your gas tank, what could that affect? Okay, keep in mind the independent variable affects another variable. So let's try and think about what variable could the number of gallons in your gas tank affect. And the variable I would put in there, I'd put how far you can drive. Okay? The amount of gas you have affects how far you can drive. And another way to think about that, so how far you can drive. So let's think about this. How far you can drive depends on how much gas you have in your tank. So how far you can drive is the dependent variable, or the independent variable of number of gallons of gas in your tank. Let's look at another situation. So if the dependent variable is your IQ, let's try and think of a variable that affects your IQ. An example I might use for that is the amount you read. I think there's lots of studies that show the more you read, the higher your IQ can get, especially at a young age. The more you read. Squeeze that in there. So I've got two variables. Remember, the independent variable affects the dependent variable, and the dependent variable is dependent on the independent variable, or it's affected by the independent variable. So your IQ depends on how much you read. Okay? Let's do another one. So if the independent variable is the number of calories you eat each day, let's figure out a dependent variable that could be affected by that. And I think the most obvious one would be your weight, because it's clear that your weight depends on the number of calories you eat each day. Let's do another one. So if the dependent variable is your level of happiness, let's try and think of what affects your level of happiness. What could be an independent variable that pairs up with this? So level of happiness depends on what? I might put in here, because I like to be active, I might put amount of physical activity. Amount of physical activity. So the more physical activity you do, the more sports you're involved in and so on, I think that will increase your level of happiness. It will directly affect that. Let's do one last example. The number of hours you study for a test, if that's the independent variable, what could that affect? What could depend on the number of hours you study for a test? And just like the previous example we had done, I'm going to put your test score here, just to try and drive that point home to you guys. Your test score depends on the number of hours you study for a test. All right. Now let's look at actually making scatter plots. Oh, I should say, I think there's one thing I forgot to mention. So I told you in the table of values, the independent variable is always on the left, and the dependent variable is always on the right. Okay? And we use X for independent, Y for dependent. If you're given it as a graph, there's a standard place that you put the independent and dependent variable as well. The independent variable always goes on the horizontal axis, the x-axis. Okay, that's why we call the independent variable x. The dependent variable, which we call y, always goes on the vertical axis, which is the y-axis. Okay, so if you're given information in a graph, the variable on the y-axis or the vertical axis is always your dependent variable, and the variable on the x-axis or the horizontal axis is always your independent variable. Okay, so now let's look at a scatter plot. Okay, so a scatter plot is a graph that shows the correlation or relationship between two variables. The independent variable goes on the horizontal x-axis, like I just said, and the dependent variable goes on the vertical y-axis. Okay, so here's your y, here's your x. And that's always the way you should have it when you make a scatter plot. There's different types of correlations. So as you make a scatter plot, you're gonna do a study and you're gonna figure out the relationship between independent and dependent variables. And you're gonna get a bunch of data points. So your data could look like anything. There could be data points anywhere. We need to know we need to know how to describe the relationship between the variables depending on what these different data points look like on your scatter plot. So if on your scatter plot, you'll notice the data goes up in a straight line to the right. Okay, we say that the scatter plot has a positive correlation when the pattern rises up to the right. So if it's clearly rising up to the right as the independent variable is increasing, the dependent variable is increasing. Okay, so it says that here this means that the two quantities are increasing together. So as this increases up to the right, okay, that's a positive correlation. Oppositely, a scatter plot shows a negative correlation when the pattern falls down to the right. Okay, so as the independent variable is increasing, the dependent variable is decreasing. Okay, that shows a negative correlation. This means as one quantity increases, the other is decreasing. And sometimes, if you do a study and you collect a bunch of information, you'll see that there's actually no correlation between the variables. So if all your points are kind of just spread out, they're not all going, they're not all increasing or they're not all decreasing. They're just kind of everywhere. Okay, then you'd say there's no correlation. Okay, correlations can also be, you can also describe them as strong or weak, depending on how spread out the points on the scatter plot are. Like these ones, they follow a very straight line, so that's a very strong correlation. Okay, they go up to the right in a very straight line, so strong correlation. These ones are still a pretty strong correlation, but they're spread out a bit more than this first one here. So this one is definitely weaker than this one is. So this is a weak negative, and this would be a strong positive correlation. Okay, next thing we need to know how to define. We need to know what an outlier is. So sometimes you'll do a study, you'll get your data, and it might look like this, and then you've got this one random point kind of out here that doesn't follow the same trend as the rest of the data did. So let's define an outlier. It's a measure that differs significantly. Measure that differs significantly from the rest of your data. Okay, so if you do your study, you get an outlier. You need to be able to decide whether you need to include that outlier in your data set or whether you can exclude it, whether you can just kind of get rid of it and ignore it. So the only time that that you can exclude, so when shouldn't you include it? The only time you can exclude it is if you can show that it's inaccurate or it doesn't represent your population. So when shouldn't you use the outlier? If you can show, I'll type this one actually. If you can show it is inaccurate or unrepresentative of the population. So that's the only time you can not use the outlier. Okay? So when do you have to use the outlier though? If you can't show that. If you can't show it is inaccurate or unrepresentative of the population. So if you can't show that it doesn't represent your population or that you measured it inaccurately, then you must include that outlier in your data set, even though it doesn't follow the trend of everything else. But if you can show that you made a measurement error, or for some reason it doesn't represent the data of the population, then you don't have to include that outlier in your data set. Okay, now let's actually make a scatter plot. Okay, a skateboarder starts from various points along a steep ramp and coasts to the bottom. This table lists the initial height and his speed at the bottom of the ramp. So we've got two variables, our initial height and our speed. If the table is horizontal like this, your independent is always on the top, your dependent is always on the bottom. And let's think about this. We could verify that. Does the height he starts from depend on his speed at the bottom? Or does his speed at the bottom depend on his height he starts at? And that's the one that definitely makes more sense. His speed depends on how high he started. Because the higher up he starts, the faster he's going to go. Okay? Because the higher you go on a ramp, the more speed you're going to gain, so the faster you're going to go. So speed depends on height. So speed is dependent, that's why we use y. Height is independent, that's why I wrote the x there. Okay, so now let's actually make the scatter plot. So I've already labeled the axes for us here. I've put the independent variable on the horizontal x-axis, and I've put the dependent variable, speed, on the vertical y-axis. Now we have to properly choose our scale. Okay, so let's first choose our horizontal independent variable scale for the initial height. So let's look at our data. The initial height, the lowest he starts is at 2, and the highest he starts is at 5. So I need my scale to go between 2 and 5. So he doesn't start anywhere between 0 and 2. So I'm going to put a break in my graph. I'm going to put a break, and use this little squiggly there to show a break. And I'm going to start the data at 2. And then I need it to go to 5. So to fit it on my graph here, I'm going to go up by 0.5 every other line here. So 2. Skip 1, 2.5, skip 1, 3, skip 1, 3.5, skip 1, 4, skip 1, 4.5, skip 1, and 5. Okay? So that'll give me the range I need to record the data. Now I need to figure out my scale for the speed. So his speed ranges between, I need to find my lowest and my highest data point. It ranges between 4.4 and 6.9. So I need my scale. I'm going to make it go between about 4 and 7. Okay, just to make sure I have enough room. So once again, I'm going to put a little break in here. That way I can start not at 0. I can start at I'm going to start it at 4. Okay, so I'm going to start at 4. And then what I'm going to do, I need it to go between 4 and 7, so I've got a lot of room here. So once again, I'm going to go up by 0.5, just like I did here. I'm going to skip a spot, then put 4.5. Skip a spot, put 5, skip a spot, 5.5, skip 6, skip 6.5, skip 7. Okay? And that's going to give me the range I need to get all of my data onto this graph. So let's start plotting our points. So here's my my initial height is 2.0. So when he starts at 2.0, his speed is 4.4. So think of that as 0.2, 4.4, and just plot that on our graph here. So at our initial height of 2, his speed is 4.4. So that's approximately right here. Next, at initial height of 2.7, his speed is 5.2. So at our initial height of 2.7, his speed was 5.2. So 2.7 is about here. His speed was 5.2. So 5.2 about here. Next point. At initial height of 3.4, his speed was 5.8. So at 3.4, about here, his speed was 5.8, which is about here. There's that point. at an initial height of 3.8, his speed was 6.1. So 3.8 is about here. His speed was 6.1. That's about here. At an initial height of 4.0, his speed was 4.5. His speed was 4.5. So that piece of data looks different than the rest of this. As his height was increasing, his speed was increasing, except for this one. So that's a little strange. At initial height of 4.5, speed of 6.5. Well, that's at a nice lattice point here, so that'll be easy to plot. 4.5, 6.5. And at initial height of 4.7, speed of 6.6. 4.7, 6.6. About there. And lastly, height of 5, speed of 6.9. Height of 5, speed of 6.9. Just about 7. Good, so there's my data. It's all plotted on the graph here. And I can look at this data and I can see, okay, as the height is increasing, as the independent variable increases, his speed is increasing. Okay? His speed is going up as initial height is going up. Okay, so it's got a positive correlation, and it's pretty strong. It follows a pretty straight line, except for this one piece of data right here. It's kind of off by itself. So this is an outlier. This right here is an outlier. Okay, if we look back to our definition of an outlier, it's a measure that differs significantly from the rest of your data. And that's exactly what this piece of information is. It's a piece of data that differs significantly from the rest. Okay, so let's just do a couple things to make sure we know everything here. Which ones are independent variable? Remember, our independent variable is always on the x-axis. So it's our initial height. And which one's a dependent variable? It's his speed. Dependent variable is always on the y-axis, his speed. And we know his speed is dependent because it depends on his initial height. Okay? The initial height affects his speed. Let's describe the relationship. Well, we've already said the higher your initial height, the faster your speed. And I also said that it's a strong positive correlation. Remember, if it goes up to the right, it's positive. If they follow a straight line, they're not too spread out, we'd say it's a strong correlation. So I might also put in brackets here, it's a strong positive correlation. Okay? Are there any outliers? Well, yeah, we discussed that already as well. I just need to give myself some room to type in here. Are there any outliers? If so, what are the possible reasons for the outlier? Well, let's think about what reasons could there be for why there's an outlier there. Why might, even though they started higher up the ramp, did their speed not why was their speed lower than it should have been? Okay, the reason I might think of maybe they fell. Okay, maybe they fell and then their bodies flying down the ramp created a lot of friction and slowed them down. So maybe the skateboarder fell. That would be one possible reason. I'm sure you could probably think of other reasons as well, but that would be the one that I would think of first. Okay, maybe the skateboarder fell. Okay. Next thing we're going to learn how to do is we're going to learn how to draw a line of best fit on a scatter plot. Okay, so there's two properties of a line of best fit we're going to need to know. I should also mention a line of best fit can help you see the relationship between variables and also to make interpolations and extrapolations. Okay, so I'll also describe to you what an interpolation and what an extrapolation is in a second as well. So properties of a line of best fit first. So there's two properties. It must pass through or close to as many points as possible. So that's the first property of a line of best fit. Second property, I'll just put down here, the second property is that there should be an even number of points on either side of the line best fit. Okay, so those are the two properties of a line of best fit. It should pass through or close to as many points as possible, and there should be an even number of points on either side of the line of best fit. Now let's define, okay, so we're going to be able to use our line of best fit to make interpolations and extrapolations. So let's define that first. Okay, and you can find that on page 71 of the textbook. Let's define them. So an interpolation, I'll do it in black here, is an estimate, or to interpolate, or to make an interpolation means to estimate a value between two measurements in a set of data. Okay? To make an extrapolation, or to extrapolate, means to estimate, I'll do it in black, keep it consistent here, means to estimate keeps changing on me. Estimate a value beyond the range of a set of data. When I show you this visually, it'll probably help as well. Okay, but to make an interpolation, that means to estimate a value between two measurements in a set of values. So in between measurements you have, so think of it as interpolation in between. Okay, so that in right there. Okay, extrapolation. Okay, to estimate a value beyond the range of a set of data. So it's extra. Okay, it's extra. So that means you're getting data outside of the data you have. So it's beyond the range of the set of data. Okay, and keep in mind these are both estimations. Okay, they're estimation techniques. So let's practice drawing a line of best fit. So remember the properties of a line of best fit. It has to pass through or close to as many points as possible, and you should have an even number of points on either side of the line of best fit. So when I draw this, when I draw my line of best fit, I want it to go through as many of these points as possible, and I want to have an even number of points on either side. So I'm going to do my best to do that. The line of best fit can start anywhere it wants on either of these axes. Okay, it doesn't have to start at the origin. I'm going to start it right about here. I want it to go through as many of these points as possible and have an even number of points on either side. So here's my line of best fit. It goes through about 1, 2, 3, 4, 5 of these points. Okay, so it goes through a lot of them, and I've got 1, 2, 3 points above the line of best fit, and 1, 2, 3 points below the line of best fit. So it meets the criteria for the line of best fit. Okay. Now, let's make another scatter plot, and after we've made the scatter plot, we'll draw our line of best fit. And after we've drawn our line of best fit, we'll make some interpolations and extrapolations using that line of best fit. Okay? So this table shows the number of paid movie admissions in Canada for 12-month periods. So I've got my two variables, fiscal year and attendance in millions. Let's first remember how to determine independent and dependent variables. Remember I told you if you have a horizontal table of values, the top row here is your x, okay, which is, no, that's a bad x. The top row is your x, which is your independent variable. And the bottom row is your y, which is your dependent variable. The attendance depends on the year. The year doesn't depend on anything, okay? Year is independent. And a good hint here, if one of your variables is a unit of time, like years or hours or minutes or anything like that, that's typically your independent variable. It's pretty safe to say that the year or the time doesn't depend on anything. That's what affects the other variable. Okay, so attendance depends on the year. So attendance is your dependent variable because it depends on the year. So attendance, dependent variable, year is the independent variable. Okay, let's make our scatter plot. First, let's remember where the independent variable goes and where the dependent variable goes. If you remember, the horizontal axis is your x-axis, and that's your independent variable. X is always the independent variable, so that's our year. On the vertical axis, your y-axis, y is always the dependent variable, so that's your attendance. I'll try and write that sideways here. Attendance. This is harder than it looks. Okay, so I've got my independent variable on the x-axis, my dependent variable on the y-axis. I'm good to go. I already gave us our scale here, save us some time. Okay, now I just want to plot all of our points. So, in 1994, they sold 83.8 million. So in 94, 83.8 million, that's approximately right here. And let's keep going. In 95, 87.3. In 95, they sold 87.3. That's almost right in the middle there. In 96, they sold 91.3. 91.3. It's approximately right there. And in 97, 99.1. 97, they sold 99.1, so almost 100 million. Let's see, in 98, 111.6. 111.6. In 99, 119.3. It's almost 120. In 2000, 119.3. So, was that the same as the last one? 119.3. Oh wait, so 99. Okay, so 99, 2000 were the same. They're both 119.3. Okay. In 2001, I guess they don't have any data available. It's okay, so I'll skip that. 2002, 125.4. 125.4. And in 2003, 119.6. Okay, so it went back down to about the same as year 2099. Okay, so now, next thing I want to do, I want to draw a line of best fit for this. So let's draw a line of best fit. Keep in mind, when I draw my line of best fit, I want to go through as many of these points as possible, and I want there to be an even number of points on either side. So this is my line of best fit right here. I'm trying to get it through as many of these points as possible and have an even number of points on either side. So I've got it through as many as I can get it through. It's through almost 1, 2, 3, 4, 5, 6. Through almost 6 of the 9 points. So that's pretty good. I've got 2 on one side, 1 on the other side. So that's a pretty good line of best fit. Okay. Next thing I want to do, I want to describe this correlation. So that line of best fit really helps here. That line of best fit shows me that as the year is increasing, so is the attendance. It's going up to the right. So I'm going to write that here. As movie attendance increases, or I should say, sorry, I said the other way around. I'll say movie attendance increases as the years increase. Okay, so that's the typical correlation here. You know, as the year increases, the movie attendance is increasing. Okay, there's no data for 2001, but we can estimate what we think the movie attendance would be using our line of best fit. So all we have to do is look at our line of best fit, go to year 2001. So go to year 2001 and go up to our line of best fit and plot a point there. I'm going to do it with a different color so it stands out. Year 2001, I'm going to plot a point on my line of best fit. And it looks like it's about, I don't know, about 120. So go across to your attendance, and it looks like it's at about right here. It's about 122 million, I'll say. So there is no data for 2001. Estimate movie attendance for this year using your line of best fit. I'm going to say about 122 million. So is this estimation that we did, was that an interpolation or an extrapolation? Look back to our definitions. Interpolation is when we estimate a value between two measurements in a set of data, and extrapolation is when we estimate a value beyond the range of a set of data. So here, we estimated a value between data. There's data to the right and data to the left. We estimated a value between there, so that's interpolation. Okay, next, estimate the movie attendance for 2005 by extending your line of best fit. So let's go to 2005. So here's 2005. Go up to your line of best fit, plot a point, and that would be your estimation. Look over to the attendance. It's about 145. So 145 million would be our estimation for that using our line of best fit. Was this interpolation or extrapolation? Well, this estimation was beyond any data. There's no data to the right here. Here's my last piece of data in 2003, okay, and I estimated beyond that. I estimated in 2005. So look back to our definition, estimating a value beyond the range of a set of data, okay, that's extrapolation. Okay, and that's it for that. Make sure you download the worksheet for these sections 2.3 and 2.4, and make sure you practice making your scatter plots and drawing your lines of best fit, and doing estimations using interpolation or extrapolation. Okay? And you can get those worksheets from jensenmath.ca, and make sure you ask me any questions if you have any.